This module is devoted to the optimal power flow, its formulation, and its applications in power system economics. In the previous model, we defined the economic dispatch and formulated this as an optimization problem, where the objective function is to minimize the cost of generation and where we enforce the following constraints. We have an equality constraint that the generation must be equal to the load, and we have inequality constraints which are. But the economic dispatch is limited in its application in power systems because in practice all the generating units and the loads are not all connected to the same bus, and an economic dispatch calculator may result in unacceptable flows in the transmission lines or unacceptable voltages at various buses in the network. Let's see how this might happen. Let's consider this very simple power system where we have two buses. At bus A we have a generator and a load, and at bus B we also have a generator and a load. And these two buses are connected by two transmission lines, and the maximum flow allowed in line is 100 megawatts. We're also given the cost curves for these two generating units, and from the figures at the bottom you can see that we have used very simple cost curves where there is no load cost, and the marginal cost of each generator is constant, and the marginal cost of generator A is $50 per megawatt hour, which is half of the marginal cost of generator B. Let's see what happens when the load at bus A is 100 megawatts and the load at bus B is 200 megawatts. We can perform an economic dispatch for this load, and because generator A is a lot cheaper than generator B, and we have assumed linear cost curves, all the load is going to be produced by generator A. So the trivial solution of this economic dispatch is PA is producing 300 megawatts while generator B is producing nothing. The result is that we have 200 megawatts flowing from A to B. That's 300 megawatts produced by generator A minus 100 megawatts consumed locally. That means that we have 100 megawatts flowing in each of the transmission lines between A and B. Now in this case, these flows are acceptable because they are below the limit on these lines, which is also 100 megawatts. So this economic dispatch solution is acceptable. But what happens if the load at B increases to 400 megawatts? Well, we can perform an economic dispatch, and because we don't hit the limit on generator A, and because it is cheaper than generator B, the solution is going to be that A should generate 500 megawatts and B should still produce nothing. So now we have 400 megawatts being exported from bus A to bus B. That means that we're going to have 200 megawatts in each of the two lines. But remember, the maximum flow in each of these lines is 100 megawatts, so the resulting flows exceed these limits, and the economic solution is not acceptable. Before moving on to the next slide, you may want to pause and think about how you might modify the economic dispatch to make it acceptable. The solution consists in reducing the output of generator A to 300 megawatts and increasing the output of generator B from 0 to 200 megawatts. So in this simple case, it's pretty easy to modify the economic dispatch to produce acceptable flows. Mathematically speaking, we can do that by simply adding an inequality constraint that specifies that we should not export more than 200 megawatts from bus A. Therefore, PA minus LA should be less or equal than 200 megawatts. Now, in a general case, that would be much more difficult to do because we would have to think ahead of time about all the inequality constraints that we might have to add, and therefore we need a more general approach to the problem. And this more general approach is what's called the optimal power flow, or OPF. The OPF is an optimization problem, and as any self-respecting optimization problem, it has to have an objective function. Now, many different kinds of objective functions can be defined for the OPF, but a classical one is to minimize the cost of generation, the total cost of generation, meaning the sum of the cost of all the generators. We also have quality constraints, and instead of having a single generation load balance for the whole system, we will have a power balance equation at each node, and therefore these will be the power flow equations, will become our equality constraints. We will also have inequality constraints, which will reflect the network operating limits in terms of line flows and voltages, and we will also have any limits that we might have on the control variables. So let's go into the details of the mathematical formulation of the OPF. Let's start with the decision variables. Well, the decision variables are all the variables over which we have some control. And the most obvious ones are the active power output of the generating units. We can also control the voltage that these generating units set, the position of the transformer taps, and if we have phase shifters, or what's sometimes called quad boosters, they also have taps we control. If there are capacitors and reactors that we can switch in and off, their status is also a decision variable. If there are power electronics devices such as HVDC and fax, we can control those. And in last resort, we can also disconnect some load, and that can also count as a control variable. So to keep things simple, we'll introduce a vector of control variables that we will label U. Our optimization problem also has state variables. State variables describe the response of the system to changes in the control variables. In this case, state variables are the magnitude of the voltage at each bus, except at the generator buses where it is controlled, and the angle of the voltage at each bus, except at the slack bus, where we know by definition it is taken as a ref equal to 0. So, to keep things simple, we define a vector of state variables that we represent by x. We also have a set of parameters which are the known characteristics of the system. These parameters are assumed constant. They represent the network topology, which bus is connected to what other buses through what lines, the network parameters, resistance, reactance, susceptance, flow and voltage limits on each of the lines, generator cost functions and generator limits, and quite a few other little things. And we summarize these parameters using a vector of parameters represented by y. I've already mentioned that the classical objective function for the optimal power flow problem is to minimize the total generation cost. Therefore, we try to minimize the sum of the cost of producing power with each of the generating units. But many other objective functions are possible. For example, it's often desirable to minimize the changes that are made in the controls, because moving too many controls is somewhat undesirable. So this could be done by minimizing over the set of all the controls the sum of the absolute value of the deviations of these controls from a reference point, and this sum might be weighted by some arbitrary cost associated with each goal. Another objective function that is often used is to minimize the system losses. And there are lots of other possibilities that have been defined, particularly in the context of electricity markets. The main and fundamental difference between economic dispatch and optimal power flow is that in the optimal power flow we explicitly take the network into consideration. We do that by introducing the power balance equations at each node, the power flow equations that we have seen before, as equality constraints in the optimization problem. These power flow balance equation will force changes in the state variables, the voltage magnitude and angles, as the control variables, for example, the power generated by the various generating unit changes. Compact expression for that will be that the function capital G of the state variables, the control variables u, and the parameters y must be equal to 0. And finally, we have the inequality constraints. The most obvious inequality constraints are those that arise from the limits on the control variables. All control variables have a lower limit u underscore and an upper limit u overscore. We also have operating limits on the flows. It's expressed as the absolute value of the flow must be less or equal than the maximum flow in the line. The absolute value is necessary because the maximum flow applies whether the flow goes in one direction or the other. And these flows will arise from the power flow equations. We also have operating limits on the voltages at each bus. And to express all of this concisely, we have a function capital H of the state variable x, control variables u, and parameters y must be greater or equal to 0. The comeback form of the OPF problem is therefore fairly simple. We want to minimize over the set of control variables u some objective function f of u of these control variables, subject to a set of equality constraints g of x, u, and y that must be equal to 0, and h of x, u, and y that must be greater or equal to 0. Don't be fooled by the simplicity of this compact expression. The OPF is a very challenging problem. There's first the size of the problem. You often have to deal with systems that have thousands of lines and hundreds of controls, and therefore we'll have to answer the question which inequality constraints are binding, and answering that question is not trivial. Also, the problem is nonlinear. Cost functions can be nonlinear, and the constraints are nonlinear. For example, the equality constraints are the power flow equations, which are notoriously nonlinear. The problem is also non-convex, and some of the variables are discrete. For example, the position of the transformer and phase shifter taps, and the status of switch capacitors or reactors are on-off variables. So how can we solve the OPF problem? Well, the earliest attempts were using gradient methods, and the idea was to build a Lagrangian function that involved the sum of the objective function plus lambda times the constraints plus mu times the inequality constraints. And then to take the gradient of this Lagrangian because it indicates the direction of the steepest ascent. And then we take the opposite direction to go in the direction of the steepest descent. And we repeat that until the gradient is almost 0, indicating that we have found an optimum. The problem is that these gradient methods have a rather slow convergence, and that the objective functions and the constraint must be differentiable. They're also difficult handling inequality constraints, because the binding inequality constraints change as the solution progresses, and it's difficult to enforce the complementary slackness conditions, which says that the mu Lagrange multipliers times the inequality constraints must be 0, and that mu must be greater or equal to 0. If you need a solution that takes into account the full AC nature of the problem, the interior point methods are probably the best approach. The idea of interior point methods, as we saw in our introduction to optimization, is that we replace inequality constraints by barrier functions, and that we progressively make those barrier functions steeper as we get closer to the solution. For this solution to work, we have to start from a point in the interior of the solution space. We need to start from a feasible solution, which may not be the optimal solution. And there are some efficient solution engines available to solve OPF in this method. But there are many cases where the full AC solution of the OPF problem is not necessary, and this is particularly the case when we're dealing with electricity markets. The idea is then that we might be able to linearize the OPF problem in such a way that we take advantage of the power of linear programming. But for this to work, everything has to be linearized. So the objective function must either be linear or piecewise linear. The equality constraints must also be linear, so we have to replace the full AC power flow equations by the DC power flow approximation. We'll see soon how that works. And the inequality constraints must also be linear. So the DC power flow approximation provides a linear relations between the injections, which are our control variables, and the megawatt line flows. But we have to limit ourselves to megawatt line flows because the DC power flow approximation does not consider the megavar flows. But there are cases where this linear programming based OPF or LP OPF is not completely satisfactory. Because of this linear approximation, the solution that we get may be somewhat suboptimal, and some of the constraints may not be respected as exactly as we would wish. So sometimes we use what's called sequential linear programming based OPF, where we iterate the solution of the linearized problem. And the algorithm would work as follows. You start by linearizing the problem around an operating point. You find the solution to this linearized optimization. Then you perform a full AC power flow at that solution to find a new operating point, and you repeat the linearization and the optimization. This LP OPF has some advantages and some disadvantages. The main advantage of this LP OPF is that you take advantage of the convergence of the linear optimization. It is guaranteed. There is a solution. It will find it. Linear optimization is also much faster than nonlinear optimization, and very reliable, fast, efficient engines are available. This is why it is used to calculate node prices in electricity markets, because in those markets you want reliability above everything else. The disadvantages is that if you want a really accurate solution, you may have to iterate the linearization, and that the reactive power aspects, for example, the VAR flows, the voltages, are much harder to linearize than the active power aspects, such as the megawatt flows. In this course, we will make extensive use of the LP-based OPF, and therefore we need to understand the linearization. The first step is to study the DC power flow approximation. We'll start from the full AC power flow equations. Remember that these equations express the power balance at each bus or node in the network. We have one equation for the active power balance and one for the reactive power balance. Let's consider, for example, the power balance at bus K. We have the injected power at bus K, that is the power injected by the generators or extracted by the loads, Pki for the active power and Qki for the reactive power. This power injected must be equal to the power flowing in and out of the bus K on the various lines connected to this bus. And we express that by the sum from I equals 1 to n of Vk, the magnitude of the voltage at bus K, Vi, the magnitude of voltage at all the other buses I, times sum of Gki cosine theta k minus theta I, which is the real part of the admittance between buses K and I, and theta k being the voltage angle at bus K, theta I being the voltage angle at bus I, plus Bki, which is the imaginary part of the admittance of the line between buses K and I, times the sine of this angle difference, theta k minus theta I. And that difference between the injected power and the power flowing in and out of the bus K must be equal to 0. And then we have a fairly similar expression for the reactive power, with the difference that the sine and cosines are exchanged. Note that if there is no direct line between bus K and bus I, GKI and BKI are 0. So we get a set of two equations for each bus, but these are nonlinear equations, and we have a set of simultaneous equations that we need to solve for the entire system. Now, we would like to transform these equations into a set of simpler linear relations so that we can perform fast calculations and occasionally get a more intuitive analysis of what's going on. And the DC power flow is going to provide us with this relation, but we are going to have to make a number of approximations. The first approximation that we are going to make is to completely neglect the reactive power aspects of the network. Essentially, we assume that no reactive power is injected, no reactive power is extracted, no reactive power is flowing at all in the network. This is a fairly reasonable approximation when the system is not very much loaded, so that there is not much need for reactive power to flow in the network. In practical terms, that means that we can simply neglect the reactive power equation at each bus K, and we're left with one equation for each bus instead of two. The second approximation that we are going to make is to neglect the resistance of the branches. This is fairly reasonable in transmission networks where the resistance of a transmission line is usually 1/10 or less than of the reactance of these lines. If we neglect the resistance of the lines, the real part of the admittance between bus K and bus I is 0. So GKI is 0. If we set that in all the equations, we are left with simpler equations that involve the injected active power at bus K must be equal to the sum from I equals 1 to n of Vk, Vi, Bki sine theta k minus theta I, and that must be equal to 0. The next approximation is to assume that we do such a good job managing reactive power that all the voltage magnitudes are equal to 1.0 per unit. This approximation goes hand in hand with the approximation of neglecting the reactive power effect in the network. Now, if we assume Vk and Vi are equal to 1 for every bus in the network, we can omit those terms in the equation, and we are left with Pki minus sum from I equals 1 to n of Bki sine theta k minus theta I must be equal to 0. Our equations are already much simpler than what we started with, but we still have this sine function, which is nonlinear. Fortunately, if an angle is small, the sine of this angle is approximately equal to the angle if the angle is expressed in radians. So in the equation at the top of the slide, we could replace sine of theta k minus theta I by simply theta k minus theta I. And therefore we are left with Pik minus sum from I equals 1 to n of Bki theta k minus theta I equals 0. And because Bki is the inverse of xki, which is the reactance of the line between k and I, we can rewrite this Pki minus sum from I equals 1 to n of theta k minus theta I divided by xki must be equal to 0. We can interpret these equations in physical terms. Pki represents, as I mentioned before, the active power injected at bus K. It is positive if there's a generator injecting power at that bus. It is negative if a load extracts power at that bus. And it can be positive or negative if there is both, depending on which one is bigger. The second term in this equation, sum from I equals 1 to n of theta k minus theta I over xki, we can represent it by pki, because it involves bus k and bus I. And pki is really equal to theta k minus theta I over xki, and we call it pki because it represents the active power flowing from bus k to bus I. So for example, in the 3-bus example that we have shown here on the right, P12 is theta 1 minus theta 2, difference in angles between buses 1 and 2, divided by x12, reactance of the line between 1 and 2. Similarly, P23 is equal to the difference in voltage angles between buses 2 and 3 divided by the reactance between buses 2 and 3, and similarly P31. You may wonder why it is called DC power flow when we're actually modeling an AC network. Well, you can make an analogy between the simplified equations and the equations of a DC network. The reactance in this analogy plays the same role as the resistance in a DC circuit. The voltage angle plays the same role as a DC voltage magnitude. Well, there is no such thing as a voltage angle in a DC network. It's just a DC voltage magnitude. And the power in the AC network plays a role of a DC current. So when we write pki equals theta k minus theta I divided by xki, it is very similar to writing that IKI, the current between nodes k and I, equals Vk minus Vi, the differences in DC voltages between nodes k and I, divided by the resistance of the branch between nodes k and I. One of the big advantages of the LP-based OPF is that, unlike the full nonlinear OPF problem, it's solved by hand. And if you're trying to solve a full nonlinear OPF, even for a small system by hand, well, good luck to you. It's just not doable. And let's take an example where we solve a linearized 3-bus example by hand. So here's our example. We have a generator connected at bus 1, a generator B connected at bus 2, and a load connected at bus 3. We are given the cost characteristics for these two generators. Generator A has a marginal cost of $10 per megawatt hour. We are assuming a linear cost curve. And the maximum output of generator A is 390 megawatts. Generator B is more expensive. The marginal cost is $20 per megawatt hour, and B can produce a maximum of 150 megawatts. If we do an economic dispatch for this example, well, because A is so much cheaper than B, A will produce its maximum power, 390 megawatts, and B will produce 60 megawatts. We need to consider what these injections will cause in the network. And the first thing that we need to know is the reactance of the branches. And to keep things simple, we will assume that all 3 lines in this small system have the same reactance. We also need to consider the maximum flows that are allowed in these branches, and I will assume that lines 1 to 2 and 2 to 3 have a maximum flow limit of 200 megawatts, while line 1-3 has a limit of 260 megawatts. And the question that we have to answer is, do these injections result in acceptable flows? Because the model that we are using in this network is a linear model, we can calculate the flows using superposition. So we can decompose the network as shown there with the injections as the sum of the network with an injection of 390 megawatts at bus 1 and a 390 megawatt extraction at bus 3, and of the same network where we inject 60 megawatts at bus 2 and extract 60 megawatts at bus 3. So the sum of these two networks gives us the injections that we have planned, and the load is 390 plus 60, 450 megawatts, as was the original load. The flow of 300 megawatt between bus 1 and bus 3 will divide itself into a flow FA and a flow FB. Now, the flow FA is going to be twice as large as the flow FB because the path 1, 2, 3 has twice the reactance of the path 1, 3 because we have assumed that all the branches have the same reactance. And we add to that the fact that FA plus FB must be equal to 390 megawatts. We come to the conclusion that FA is 260 megawatts and FB is 130 megawatts. We can do the same thing with the injection of 60 megawatts at bus 2 and the extraction of 60 megawatts at bus 3. The flow FC will be twice as large as the flow FD because the pass 2, 1, 3 has twice the reactance of the pass 2, 3. And we also have SC plus FD equals 60 megawatts. Putting those two observations together, we come to the conclusion that FC is 40 megawatts and FD is 20 megawatts. We can now put things together as called for by superposition. So let's first look at the flow in line 1, 2. Flow in line 1, 2 is going to be 110 megawatts because we get 130 megawatts flowing from 1 to 2 from the 390 megawatt injection and 20 megawatts flowing from 2 to 1 for the 60 megawatt injection. In line 2, 3 we have a flow of 170 megawatts resulting in a sum of 130 megawatts from the first part and 40 megawatts from the second part. In line 1, 3, we have a flow of 280 megawatts, which is 260 plus 20 megawatts. Now notice that I put the flow in line 1, 3 in red because it exceeds the maximum allowed flow in this branch, which is 260 megawatts. The flows resulting from the economic dispatch are therefore not acceptable. We must reduce the flow in line 1, 3 by 20 megawatts. And how can we do this? Well, we're going to have to combine some reduction on one of the generators with increase in the other. In particular, if we reduce the injection at bus 1 by 1 megawatt, we must increase the injection at bus 2 by 1 megawatt to keep the load generation balance. Now, let's observe that if we decrease the injection at bus 1 by 3 megawatts, 2 of these megawatts are not going to flow in line 1, 3. One of these megawatts is not going to flow through the other path. On the other hand, to compensate, we increase the injection at bus 2 by 3 megawatts. Well, one of these megawatts is going to flow on line 1, 3, and the other 2 are going to flow in line 2, 3. So a combination of decreasing the injection at bus 1 by 3 megawatts and increasing the injection at bus 2 by 3 megawatts is going to decrease the flow in line 1, 3 by 1 megawatts. So if we want to achieve a 20 megawatt reduction in the flow on line 1, 3, we need to shift 60 megawatts of injection from bus 1 to bus 2. Let's check the resulting flows using superposition again. If we inject 330 megawatts at bus 1 and extract 330 megawatts at bus 3, 220 megawatts will flow from 1 to 3, and 110 megawatts will flow from 1 to 3 via bus 2. If we inject 120 megawatts at bus 2 and extract these 120 megawatts at bus 3, 80 megawatts will flow directly from 2 to 3, while 40 megawatts will take the long way around, which has twice the reactance, and go from 2 to 1 to 3. Let's put that together. We get 70 megawatts flowing on line 1, 2, which is 110 megawatts from 1 to 2 minus 40 megawatts flowing from 2 to 1. We get 190 megawatts flowing from 2 to 3 directly. That's 110 megawatts plus 80 megawatts. and we get 260 megawatts flowing from 1 to 3, which is exactly the limit on this flow. Let's discuss this OPF solution. The first thing to observe is that the OPF solution is more expensive than the original economic dispatch solution. In the economic dispatch solution, we are producing 390 megawatts with generator A, which has a marginal cost of 10, and 60 megawatts with generator B, which has a marginal cost of 20, for a total of $5,100. In the OPF solution, on the other hand, we are producing only 330 megawatts with generator A at $10 per megawatt hour, and 120 megawatts with generator B at $20 per megawatt hour, for a total of $5,700 per hour. The difference between these two costs is what's called the cost of security, and in this case it's $600. Cost of security because we have adjusted the output of the generators so that our network remains secure. Another thing to observe is that the constraint on the line flow is satisfied exactly. We did try to go below the limit on the flow of this line because that would cost us more. We would have to shift more generation from the cheap generator A to the more expensive generator B if we want to reduce the flow below the limit. The second thing to observe is that we have used an ad hoc method to solve this problem. In practice, there are systematic techniques for calculating the sensitivities of line flows to injections, and these techniques would then be used to generate constraint equations that would be added to the optimization problem and that would be fed into an LP optimization engine. The conventional OPF that we have just described only guarantees that the operating constraints are satisfied under the normal operating conditions. For example, it assumes that all the lines are in service and will remain in service. Now, this does not guarantee security. To guarantee security, we must determine an operating condition that remains stable after any -1 contingency. And that leads to the definition of what's called security constraint OPF, that considers not only the base case conditions, but also security constraints that reflect these n-1 contingencies. So let's go back to a 3-bus example. The base case solution of the OPF is fine because none of the lines is overloaded. But we have to consider what happened under contingency conditions. For example, if lightning strikes the line between bus 1 and bus 2, and this line trips, the 330 megawatt produced by generator A are all going to flow on the line between 1 and 3. This will overload the line, and under these contingency conditions, the system will not be stable because this line 1-3 would then soon trip. Therefore, this OPF solution does not satisfy the security constraints. Let's formulate the security constraint OPF. We start with the objective function, which consists in minimizing the cost of the control action U under the base case conditions. This optimization is done subject to equality constraints, which are our power flow equations for this base case, G of x naught, U naught, Y naught must be to 0, and some inequality constraints which reflect the operating limits for the base case, H of x naught, U naught, Y naught must be greater or equal to 0. We also need to consider equality constraints for the contingency case K, J of xk, U naught, Yk equals 0, and H of xk, U naught, Yk greater or equal to 0, which represent the operating limit for the contingency K. So, under contingency K means that a line may have been disconnected, therefore the parameters of the system Yk are different from the parameters of the system Y naught under the base case conditions. That leads to a change in the state of the system xk, but we keep the control variables u0 constant. Now we get a set of equality constraints g of xk u0 yk equals 0 for every contingency, and a set of inequality constraint h of xk u0 yk also for each contingency k. This formulation of the security constraint OPF implements what's called preventive security, because we assume that the control variables u0 do not change between the base case, which is the state where we expect to operate, and the contingency cases, which are the state that might occur if a contingency does develop. So we have u0 appearing in the contingency constraints. Now there are many contingencies where it is not unreasonable to expect the operators to react to the contingency to adjust the controls so that the state of the system after the contingency remains acceptable. In those cases, we no longer have to assume that the control variables remain at the values used not after the contingency has occurred. So we can introduce for each contingency a set of controls UK that we can try to determine using the security constraint OPF. And in this case, the equality constraint for the contingency K involve XK, UK, and YK, and the inequality constraints for the contingency K are also a function of XK, UK, and YK. However, there is a limit to what the operator can do. There are some maximum deviations that can be implemented on a generation dispatch, because it does take a while to redispatch generators and there's only a certain amount of time available before a line overload, for example, has to be corrected. Therefore, we have to add one more constraint, or one more constraint for each contingency, that says that the maximum change in the control variables UK minus u0 must be less or equal than a pre-specified maximum change. So this formulation implements what's called corrective security, because we expect the operator to implement corrective actions after the contingency has occurred. As I mentioned, this last equation limits the change that can take place to what can be achieved in a reasonable amount of time. On the other hand, the objective function considers only the value of the control variables in the base, because most of the time the contingencies will not occur, and really what we have to worry about is the cost of operating the system in the base case. The security constraint OPF is a formidably challenging problem, mainly because of its size. Let's take an example. Recently, there have been projects to try to develop security constraint OPF tools that would be able to handle the whole European transmission network. Now, that network involves some 13,000 buses. That means we have 13,000 voltage constraints, and 20,000 branches. That means we have about 20,000 flow constraints. Now, if we only consider line contingencies, and implementing n-1 security means that we have to look at 20,000 contingencies. So in theory, a naive approach to the security constraint OPF means that we would have to consider 20,000 times 13 voltage constraints plus 20,000 line flow constraints, which is about 660 million inequality constraints. Now, that naive approach is obviously way beyond what any powerful solver can handle. However, it's pretty clear that not all contingencies are going to create limit violations. Some lines will be lightly loaded at any time, and therefore the contingency on these lines will not create any real problem. Another thing is that some contingencies will have only a local effect. For example, if a line trips in Poland, it's unlikely to have an effect in Portugal, and you don't need to look at the whole network for every possible contingency. The N-1 criterion has the main advantage that it is very simple and relatively straightforward to implement. However, it has some major limitations. For example, not all contingencies have the probability. For example, the lightning is much more likely to strike a long line rather than a short line, simply because of its length. And the probability of a contingency is much, much lower in good weather as opposed to bad weather. Also, not all contingencies are going to have the same consequences. Some contingencies might create a local undervoltage situation, and others could put the system on the edge of stability limits. Therefore, the simplicity of the N-1 criterion does not always translate into a good measure of security. Now, another aspect is that some of the N-2 conditions that we do not consider because it is assumed that losing two components of the system at the same time is not credible. Well, these N-2 conditions are not always not credible because some of these outages are not statistically independent event. One N-1 contingency could actually trigger another one, and then you are in an N-2 condition which has not been taken into account by the security constraint optimal power flow. So the conclusion is that the N-1 criterion does not ensure a consistent level of risk, where we define risk as being the product of probability and consequences. Probability of a contingency occurring and consequences measuring the severity of what might happen if this contingency does occur. These limitations of the N-1 security criterion have spurred some interest in what's called probabilistic security analysis. And the goal of probabilistic security analysis is to operate the system at a given constant risk level. However, this is not going to be an easy thing to implement. For example, first challenge is that how do we identify the probabilities of non-independent events, these N-2 conditions that I mentioned on the previous slide. These non-independent events are typically triggered by failures in the information technology that surrounds the power system, and those compounds the electrical failures caused, for example, by lightning strikes. Another challenge is how do we estimate the consequences of a contingency? For example, one way of measuring the consequences is to say, okay, this might lead to a blackout, but what portion of the system would be blacked out if this N-2 condition were to occur? And finally, we have to decide, okay, what would we do if we determine that this constant risk is not achieved? What preventive measures would we take? And the number of possibilities is vast, and choosing the right one is going to be extremely challenging.